So we shall start with vector algebra. Okay, vector algebra. I mean, you might have gone through this one in class 11th and 12th. Okay, the same vector algebra we will discuss here in the first class. But I will give the orientation towards whatever the topic we are going to discuss later. Okay, I mean, whatever the mathematics I discuss here, I will slightly orient towards what you call electrodynamic syllabus. Is that okay? Yes. So how do you define a vector? How do you define a vector? Quickly. Vectors, isn't it? So again, we can define vectors as it is a quantity which has both direction as well as magnitude, isn't it? And we define scalars as a quantity which has only magnitude, isn't it? Scalars, which is a quantity which has only magnitude. Yes. Now, again, usually in class 12th, we define vectors as a quantity which has direction and magnitude, isn't it? But that definition is not complete. Okay, that definition is not complete. So, because let me raise some questions here. Okay, yeah, if you define vectors as a quantity which has direction and magnitude, so let me ask one question here. Yeah, you said what you call vectors are the quantity which has direction and magnitude, isn't it? So let me ask a question. What is electric current, whether it's a vector or scalar? Electric current, whether it's a vector or scalar. It's a scalar. But it has direction. Electric current has a direction. It has a magnitude, isn't it? So in terms of ampere or milliampere, we say, isn't it? What is electric current, whether it's a vector or scalar? It has direction, isn't it? Speak out.
Sir, it does not follow parallelogram law of vector.
Yes. Again, so about current, am I right? It seems to be a vector, isn't it? Because it has direction, it has magnitude, isn't it? Now we shall take one idea here. Okay. Suppose you have a current I1, I2 here. Okay. You have a resultant current here. Is that okay? It is a node. This is current I1. This is current I2. Is that okay? So let me take this one as I3. In case of current, okay. So how do you write I3? Again, how do you write law here? Kirchhoff current law. We call like that. Am I right? I3 is equal to I1 plus I2, isn't it? This is how you write. So now this is a law of addition of what you call current here, isn't it? So let me similarly take law of addition of vector here. I hope you know that one. Okay. Triangular law of addition. Let me take this one. Okay. Vector A here. Vector B here. Is that okay? So this is A plus B, isn't it? This is A plus B. Vector C, that's equal to A plus B. Is that okay? We write vector C is equal to vector A plus vector B. Okay. Now look at this one. In this one, this vector C that depends on magnitude of A, magnitude of B. Okay. Suppose if you increase length of A, this vector C will change. Am I right? If you increase length of B, then this vector will change, isn't it? As well as it depends on the relative orientation. Am I right? It depends on direction of A. It depends on direction of B, isn't it? If you change direction of A, this vector C will change. If you change direction of B, again this vector C will change, isn't it? So that's why again, so this is a law of addition of vector. We call this as triangular law of addition of vector, isn't it? So vectors are the quantity which has direction and magnitude, along with it should follow some addition rule. Okay, it should follow some rule of addition. Is that okay? Law of addition. So now again you can see here what is the again here also you have one addition rule, here also you have one addition rule, isn't it? So can you find the difference? Suppose if I bend these two wire, will this rule changes? Yeah. So these are so that's why again current, electric current, they add like a scalar. Look at here, the word came, isn't it? So there are quantities which has both direction and magnitude. Again, while adding that one, you should follow some rule. So this is the rule, this is the law. Is that okay? So again, the resultant vector that depends on individual vector direction. Suppose if you change B, so can you so can you imagine how vector C will change, isn't it? If you change the length also, obviously resultant changes. That happens here also, isn't it? If you change individual magnitude, then definitely resultant will change here also. If you change individual magnitude, then the resultant will change. Not only that, it depends on the orientation also, isn't it? If you change the magnitude, look at here, one more thing you need to observe. If you change the magnitude of A or magnitude of B, this C orientation also changes, isn't it? So that's why, so vectors are the quantity which follow this kind of rule. Again, while adding that one, we should follow some rules. So this is one of the rules. Okay. So scalars are the quantity which do not follow any additive rule. You simply add them. Suppose you take two masses, M1, M2. Okay, what is the total mass? Total mass is equal to M1 plus M2. Isn't it? There is no individual orientation or something for that quantity called as mass, isn't it? We call them as a scalar. They add like a scalar. Is that okay? So again, while adding that one, again, it is scalar because of that. It doesn't depend on any direction or something. You don't have to follow any rule, you just add them. But here you need to follow some rule, isn't it? So that's why vectors are the quantity which has a direction and magnitude. Okay. Along with that, you should follow some addition rule. So can I write it like this? Here there are no rules. You are simply adding, isn't it? But here there are rules to add them, isn't it? So you have to, if you have vector A, if you have vector B, you have to take vector A as one side of the triangle, vector B in other side of this triangle, and so third side will be the resultant, isn't it? This is the rule. Is that okay? This is not following that rule, isn't it? You are simply adding that, isn't it? So that is the difference between scalars and vectors. Okay. So that's why, along with this direction and magnitude, you should point out two more things for vectors. Okay. So that is, they should follow some addition rule. Rule or law, okay, whatever. Along with that, let me write one more thing. I may not address that one. They should follow some transformation rule. Okay, when you change the coordinate system, okay, usually our scalars, okay, if you take mass, charge, density or something, they will not change, am I right? They are independent of coordinate system. Coordinate is always our choice, isn't it? But if you change the coordinate system, vectors will transform actually. They will change sometimes. Is that okay? So that's why, again, along with that, so again, this is also one more important property of vector. Okay? Or vectors should be defined like this actually. So this is incomplete, okay? If you define vector which has the direction and magnitude, this is very incomplete. You should add, they should follow some addition rule. Along with that, so they should follow some transformation rule. So we shall see that one, okay? If time permits, we shall see this where we use this transformation rule in electrodynamics, okay, at the end of the syllabus. So shall I start? Now look at here. We shall list out what are the, laws, rules, whatever I told. Is that okay? So let me start with that one. Addition of vector. So addition of vector, first one. So shall I rub it out? They should follow some addition rule and they should follow some transformation rule. That means, transformation means if you change the coordinate system, okay, how vectors changes, okay. So that also defines vector actually, okay. If you change the coordinate system, how quantity changes, that defines a vector actually, okay. Yes. So any question here quickly? Now let me take addition of vector. Addition of vectors. addition of vectors. Okay, again I hope you know, again I have already taken, isn't it? So if you take this one as vector A, okay, if you take now look at here, one more thing you need to point out, vector usually do not have a proper location. Okay, they do not have prior location. Okay, I mean you can have vector A here, you can have vector B here. Is that okay?
No, sir. I mean, if some point will be there, then
No, again, while defining this abstract mathematics, you don't take any what you call proper location. Okay, if you discuss some electric field, magnetic field, then you define electric field at some position, magnetic field at some position. That's a different story. Okay, usually while defining abstract mathematics, again, we don't take any what you call so particular location. Okay, vector we don't take any prior location. I'm not talking about vector field. I'll come to that point later. Is that okay? Simply a vector which has a direction and magnitude, isn't it? No prior location. Okay, no prior location. That's why. So suppose if I have vector A here, vector B here, if I want to add these two, I have to take this vector here. Is that okay? I have to take this vector here. Is that okay? So then the third side of this triangle, the third side of this triangle, that's equal to C, is equal to A plus B. We call this one as triangular law of vector addition, isn't it? You know this one. And there is one more law. Okay, suppose if you have vector A, vector B, okay, take vector A here, take vector A here. Okay, so take this vector like this here, as a side of parallelogram actually. So take this vector like this here, take this vector like this here. Is that okay? Vector B here, and draw a parallelogram. Just what you call extend this one and draw a parallelogram here. Is that okay? Draw a parallelogram here. Then the diagonal of the parallelogram is the resultant. C is equal to A plus B. This is a parallelogram law of vector addition. I hope you know that one, isn't it? Obviously, you can see here, if you change the direction of A, isn't it, then this diagonal will change, isn't it? Diagonal and its magnitude as well as direction changes, isn't it? I think magnitude may not change. Am I right? If you just change the direction, if you enlarge A, then definitely this diagonal length will change, isn't it? So like that. Again, it depends on magnitude of A, magnitude of B. It depends on direction of A. It depends on direction of B. It depends on relative what you call angle, isn't it? I mean the relative orientation, isn't it? Resultant C is equal to A plus B. C is equal to A plus B. Okay, that depends on magnitude of A, magnitude of B, direction of A, direction of B, or so you can say like that depends on relative what you call orientation. Am I right? I mean the angle between them, isn't it? So again the resultant that depends on angle between them also, isn't it? Like that. Obviously you know this one, isn't it? Addition of a vector, it's very elementary. Shall I repeat out? Just read out the book, okay, after the class. Not a big deal, okay? Addition of a vector is commutative. Okay, vector A plus vector B is equal to vector B plus vector A. Is that okay? Addition of a vector is commutative. And it is associative also. Okay, vector A plus vector B plus C. Okay, order of addition doesn't matter, isn't it? That's what associative law says, isn't it? Vector A plus vector B plus vector C. Is that okay? Now let me take one more idea here. Subtraction of a vector. subtraction of a vector. Okay, suppose I have some vector A here, I have one more vector B here. Okay, now I have to find A minus B. I have to find vector A minus vector B. We can do it by addition of A with minus B. Okay, I think I didn't define this one. Vector can be multiplied with a scalar. Okay, if you multiply that one by a scalar, its length will change. Sometimes if that scalar is negative, vector will invert. Is that okay? Suppose if you have vector A here, okay, if you multiply minus 1, scalar minus 1, okay, so that will be minus A. Is that okay? I have multiplied scalar minus 1 here. Is that okay? So multiplying by minus 1, it will not change the length of the vector. Lengths are almost same. Is that okay? But it will invert the direction. Is that okay? I hope you can grab that point. So that's why A minus B, what I am going to do here is I'll take vector A, I'll add minus B to vector A. Okay? This is what I always feel comfortable. In case of subtraction of a vector, I will convert that subtraction into a kind of addition. Is that okay? A minus B can be written as A plus of minus B. I will define minus B vector. I will add that one to A. Is that okay? This is B vector, am I right? Can I define minus B? This is minus B. Is that okay? Minus B vector. Minus B plus A or A. Or A plus of minus B, isn't it? Because it is commutative, isn't it? I can write A plus of minus B, that's equal to minus B plus of A, isn't it? Because it is commutative. So minus B vector plus A vector, what is the resultant? Speak out. This is the resultant, am I right? According to our triangular law of vector addition, isn't it? Speak out. So that's why this vector can be considered as A minus B or A plus of minus B or minus B plus A, whatever. Is that okay? I have vector A here, I have vector B here. These were my vectors, okay, initially. I have vector A here, okay, I have vector B here, okay. I wanted to find A minus B. I inverted vector B, okay, minus B, I added to A. Is that okay? Yeah. Usually, look at here, you will do this one very often, okay. You will have vector A here, okay, you will have vector B here, okay. You will have vector B here. Now, you need to find A minus B, isn't it? Again, many cases you will have vector which are written like this, whose tails are coincided, okay? Then you need to find A minus B. Or, so again, I'm just thinking about further syllabus, okay? I mean further part of the syllabus. You may need this length sometimes, okay? This length. Then what will you do? Can you grab this idea? Isn't it? You have one vector A, you have other vector B. You need this length or this vector here, which connects their ends, isn't it? Then you have to go for A minus B. A plus B will not give that. A plus B is this one, okay? You can use so parallelogram law of vector addition. A plus B is a kind of diagonal one. Is that okay? But when you need this distance or when you need this vector from this point to this point, you should go for subtraction of a vector. Is that okay? You are going to apply this one, okay? So remember. Now look at here. So can I write, if this is B, can I take this one as minus B? Is that okay? Minus B. Minus B plus A. Okay, minus B plus A. According to your triangular law, you can draw like this. What is this one? Minus B plus A. Is that okay? So this is a vector A minus B. or minus b plus a. You are going to use this one occasionally, okay? And you should be able to write that one quickly. If you have vector a here, if you have vector b here, invert vector b and use law, so triangular law of vector addition, quickly write this vector. You are going to apply that one later. Is that okay? Speak out. Now, multiplication of a vector by a scalar, I have already taken here, okay? Multiplication of a vector by a scalar, let me take that one as a kind of second property or something, okay? So scalar means again real quantities, okay? Real numbers or something, okay? Not complex quantities here. We are talking about real vectors here. Is that okay? So now again, so you can, if you have a vector a here, okay? Then I will multiply a by 2. 2 is a number, am I right? I will multiply vector a by 2. Then what will happen? So this 2 will change its magnitude actually. It will double the magnitude. Then how do you represent that vector? You have to draw similar vector, but you have to double the magnitude. This is 2a. If this is a vector, this is 2a vector, whose direction is not changing, but its length is doubled. Is that okay? Suppose if you have a vector a, if you multiply by minus 1, as I have taken already, isn't it? Minus 1 into a, then how do you write that vector? You have to keep the length same, almost same. Is that okay? You have to keep the length same, but you have to change the direction. Is that okay? So this is again how we can multiply vector by a scalar. Don't multiply by a complex number, okay? We are talking about a real vector.
If I multiply 0,
it will become a null vector. Let me talk about that one, okay? If you multiply a vector by a scalar 0, it will become a null vector, okay? Whatever the scalar you multiply, it will become vector only, isn't it? Whatever the scalar you multiply, if you have a vector a, if you multiply by a scalar, so that is also vector only. Is that okay? Whatever the scalar you take. If you take that one as scalar 0, then it will become null vector. Let me define that null vector. It's a very good question, okay? Now again, along with this, you can define again, vector can be multiplied with the scalar. It will change the, if that scalar is negative, it will invert the direction. If that scalar is positive, it will rescale that one, or it will change the magnitude, isn't it? That's very simple. So if you have two vector a plus b, okay, addition of two vector, if you multiply that one by a constant scalar, okay, then it will be like this, c into a plus c into b. I hope these things are obvious for you, isn't it? Or if you have like this, a plus b, a and b are scalar here, okay, a and b are scalar, multiplied with vector a, you can write as a into vector a plus b into vector a, isn't it? You can write this kind of property. And logically you can show that one. If you take one vector addition, okay, you can logically show that one. I'll not go for any mathematical proof here, okay? I'll make it logical, and we shall concentrate on application of this, okay? Now, as you asked, null vector, isn't it? Null vector. Okay, null vector. Let me ask one question. What is the magnitude of null vector? Speak up. What is the magnitude of null vector?
0, sir.
0. What is the direction of null vector?
No direction.
No direction. Then why do we need that one? You said vector has both direction and magnitude, isn't it? But null vector has no direction. It has magnitude 0, it has no prior direction, then why do we need that one? If you have 4 apples and 5 apples, okay, how many total number of apples you have? You have a basket of 4 apples plus a basket of 5 apples, okay? How many? So what is the total number of apples you have? 9 apples, isn't it? So again, apple plus apple is equal to apple. 4 apple plus 5 apple is equal to 9 apple, isn't it? So if you have 4 apple, 5 banana, will you say 9 apple? No, isn't it? Apples are added to, again, become apple, isn't it? You can't add apple to banana, isn't it? Are you getting a point? So like that, you can't add scalar to a vector. That is meaningless, isn't it? If you add a scalar to scalar, you will get other scalar, isn't it? If you add a vector to vector, you will get other vector, isn't it? Now you will end up with a situation. Suppose if you have a vector A, if you add a minus A to that one. Now you are adding vector. What should be the resultant? Resultant should be a vector, isn't it? Are you getting a point? According to this rule, resultant should be a vector, isn't it? But what is the magnitude of the resultant? 0, isn't it? A minus of A, isn't it? Since resultant is a vector, okay, but its magnitude is 0, that's why we defined a null vector. We can't write scalar 0. If you write scalar 0, that would be wrong. How vector added to become scalar? Isn't it? Vectors added to become, again, it should become a vector, am I right? When you add vectors. That's why we define a null vector. Remember, you will end up with this situation. Is that okay? You will end up with this situation and you need to define a null vector, which has no prior direction actually, 0 magnitude, okay? But still we need to define that one, isn't it? To what you call, to differentiate this one, am I right? Suppose you have 2 minus 2, how do you write? You will write 0, scalar 0, isn't it? So there is a difference between these two, am I right? There is a difference between these two, am I right? These are vectors which are added. These are scalars which are added, isn't it?
But still we don't have the direction of null vector. Then how do I differentiate this scalar 0 and vector 0?
No, again, mathematical, or this doesn't have any physical significance actually. To how to say? So to avoid that mathematical ambiguity or symbolic ambiguity, are you getting my point? Vector plus vector should be a vector. Scalar plus scalar should be a scalar, isn't it? You have scalar 0, you have vector 0, isn't it? To differentiate that one, you need to define null vector properly. Are you getting my point? It's about to differentiate symbolic ambiguity. Are you getting my point? So again, if you just write this one as 0, so what is the difference between this one and a scalar 0, isn't it? Or how does scalar comes when you add a vector? Tell me. Isn't it? So that's why there is a necessity of defining a null vector, okay? Let me call this one as a null vector, which has no physical significance actually, okay? You can't give any physical or geometrical significance for that one, because it has no prior direction, isn't it? But it is very necessary, it is very required to define that one, okay? You have to define a null vector, and that is used like this. This is one of the examples. Later we shall see. So cross product between vector, okay? A cross B is a vector, am I right? If you take cross product with itself, what is this one? Cross product is a vector, am I right? What is cross product with itself? Will you write 0? No, it cannot be scalar, it should be a vector. We said cross product is a vector, isn't it? We write null vector. Is that okay? To differentiate, we need to define that one. Is that okay? Speak out. We say cross product is a vector, am I right? If you write cross product with itself vanishes, will you write scalar 0? That would be wrong, isn't it? Because you said cross product is a vector. That's why you have to define it as a null vector.
I got a lot of in books. They are simply 0.
No, they may write the 0, but that is not 0, okay? If you see Griffith's electrodynamics book, he will write bold letters. For null vector or for vectors, he will write bold letter. You should take care, because it is defined. Why would mathematician would define null vector, isn't it? Because again, when you have a resultant which is a vector whose magnitude vanishes, okay, then you need to define it as a what you call null vector, isn't it? And it has no prior direction also, no physical significance. But to differentiate it from scalar 0, you need to define a null vector. Is that okay? Speak out. So null vector is very much necessary. Is that okay? Multiplication of a vector by a scalar. Now, next one, which is very important, third one, dot product. Okay, dot product. We have, again, you know most of it. Let me make it very simple. Okay, A dot B. Okay, vector A dot vector B. That's equal to, how do you define this one? Dot product. Magnitude A, magnitude B. Let me take this as magnitude. Okay, if I'm not keeping any arrow, that is a magnitude. Take it as a magnitude. Okay, A B into cos theta. What is theta? Theta is the angle between A and B. Isn't it? You have vector A here, okay, you have vector B here. You need to take a dot product, okay. While taking dot product, one thing you need to remember, you have to place this vector so that their tails of this vector coincide. You have to draw this vector like this. Is that okay? So then only, again, you can so now whatever the theta here, that is this angle actually. Is that okay? That is this angle. When you place those vectors so that their tails are coincided, then you can define that angle theta. Or theta is the angle between the vector when the tails are coincided. Is that okay? That's a proper what you call so definition of theta. Is that okay? Now again, A dot B, dot product between A and B, or scalar product. It's also called a scalar product, isn't it? It is written as magnitude A, magnitude B, and cos of the angle between them. What is the angle? Angle is measured when their tails are coincided. Be careful. Is it okay? Suppose if you have a vector A, okay? If you have vector B, then how do you define angle theta between A and B? Speak out. Yeah, speak out. You have to redraw this one. You have to write A, okay? You have to take this vector like this. You have to what do you call? You can move that vector. Okay, it has no location. Okay, you can move that vector like this, don't it? You have to move that vector like this. Vector B. Then this is the angle theta that we are talking about here. Is that okay? Speak out. While taking dot product, don't take this angle. That would be wrong. Is that okay? No, whatever. Again, A to B, B to A. Angle is same here. Is that okay? No. Again, so cos of 180. Again, so this would be what you call, so 360 minus theta. Am I right? That is cos theta only. Cos of 360 minus theta, cos theta only. It will give that one. But while you wish to take this angle, no, you can take, that is 360 minus theta. Can I say like this? Cos of 360 minus theta is cos theta only. Okay. So it doesn't matter. But this is not the angle. Okay. If vector A is like this, vector B is like this, this is not the angle that we are talking about here. You have to redraw the vectors. Okay. You have to change its location in such a way that the tails, these are tails. This is head. This is called as head. Speak out, anyone? Which is head? Which is tail for a vector? Arrow is head. Am I right? This is tail. Am I right? You have to draw the vector so that the tails are coincided. Then only you can define the angle between the vector. This theta is the angle between the vectors when the tails are coincided. Is that okay? So then you can take a dot product, and that dot product is defined as magnitude A, magnitude B into cos of the angle between them. Okay. Now we shall see what it means geometrically. Okay. What it means geometrically. So I have vector A here. I have vector A here. I have vector B here. Is that okay? Angle theta is between them. Is that okay? Now let me take a projection here. Let me draw a perpendicular here. Is that okay? From this point to, so vector A. Is that okay? Now, what is this distance according to our trigonometry? Speak out. What is this distance? What is this distance? Speak out.
B cos theta.
This is length B, am I right? Magnitude B into cos theta, am I right? That's equal to B cos theta. B cos theta. Now, if you see the dot product, that is B cos theta, that is multiplied to A. B cos theta is a projection length. Can I take like this?
Yes,
Or
sir.
wait a second. Let me give one mathematical terminology. We call that one as scalar projection actually. Scalar projection. There are two type of projection. One is vector projection. Another one is scalar projection. Okay. Or can I call it as a projection length that I feel comfortable? Okay. Length of the projection. Is that okay? That's equal to B cos theta, isn't it? Now that length of the projection multiply with length of A, isn't it? That's it. That's the dot product. Here we can say only that one because we are discussing abstract vectors here, isn't it? We don't have any physical, these are not physical quantity. We haven't, modeled this one, isn't it? That's why. So again, if you want any geometrical meaning of that one, B cos theta is a projection length of the projection of B on A. We say like that, okay? This is the length of the projection of B on A. Can I say like this? And that projection length that is multiplied with magnitude of A. That's it. Is that okay? That is the dot product. And you can see in a different way also. Am I right? You can see in a different way also. You can write as B A cos theta. Is that okay? You can draw a projection of A on B, isn't it? Like this. Where this length is A cos theta, isn't it? Take out. This is theta, this is A, this is perpendicular, is that okay? Then this length is A cos theta. A cos theta multiplied with length of B. You can think like that also. Is that okay? So this is a dot product. And you can see here, A dot B is equal to AB cos theta. That's equal to BA cos theta. Can I write as B dot A? We say it is commutative. A dot B is equal to B dot A. A dot B is equal to B dot A. Is that okay? Now two things are there here, okay? A dot B is equal to AB if theta is equal to 0, isn't it? Cos 0, 1. Is that okay? Now look at here. If A and B are the vectors other than null vectors, okay? They are not null vectors, okay? Let me take two vectors, they are not null vector. So, and if A dot B is equal to 0, scalar 0, are you getting my point? Dot product is a scalar, these are scalar, is that okay? Scalar 0. If A and B are vectors other than null vector, okay, they are not null vector, but the dot product vanishes, okay, then A is perpendicular to B. Be careful while defining that one. Look at here. So among A and B, if one of them is a null vector, then also dot product is 0, isn't it? So let me take a vector which are not null vector, and if dot product between them vanishes, then we say they are perpendicular. Scalar 0, okay? Dot product is a scalar. You know that one, isn't it? Scalar product. Let me take one more thing, very important one. Okay. If you have a vector A, okay, if you have a vector A, if you take dot product with itself, what would you get? A into cos 0, isn't it? Pick out. Angle between these two is 0, isn't it? So that's why that's equal to magnitude of A into magnitude of A. That's equal to magnitude of A the square, isn't it? Just grab the idea. Just grab the idea. You know this one. You know this one. Okay, these are logical. Okay. Yes. If you take dot product with itself, you will get length square actually. I'm going to use this one very occasionally. Okay. Whenever I need a length of the vector, I'm going to take dot product with itself. Can I call it as dot product with itself? Okay. Let me write this A square as A dot A, or let me write A as under root of A dot A. I think we call this one as norm of a vector in linear vector space, isn't it? Whenever I need magnitude of A, okay, I'll take dot product with itself and I'll take a root. No, that is again, that we write like this, norm of A. That's it. There is other symbol. Both are same. I'm talking about magnitude here. Norm is nothing but magnitude or length, isn't it? We don't call it as length, we call it as magnitude of a vector. Or you can call it as length of a vector also. Okay, no issue. Is that okay? Some basic ideas. I hope you know most of this, okay? Now, as I told, whenever we discuss this projection, these small, what you call, ambiguity in terminology may arise, okay? Vector A here, vector B here, okay? If I draw a perpendicular here, what is this one? This length is B cos theta, am I right? If this is theta, this length is B cos theta, isn't it? Now, there are two things here, okay? One is, again, so let me quote pure mathematics. Vector projection, okay? Vector projection. Projection of B on A, okay? Vector projection, that is this vector actually. Vector projection, okay? We call this as vector projection. Or again, I hope you have worked out some vector algebra. I mean, you can split that vector into two orthogonal components, isn't it? You can split this one like this, isn't it? One is horizontal component, one is vertical component, like that, okay? It's very similar to that one, okay? So again, we have taken this length is B cos theta, am I right? This length is B cos theta. I have taken that one as a projection length, am I right? Or scalar projection, okay? We have one more thing, vector projection here, okay? Projection of B on A, okay? We call that as vector projection. How do you write this vector? Whose length is known? Speak out. Length is known. How do you write this vector?
So in the form of unit vector.
Now again, so this vector has a length which is B cos theta, am I right? What is the direction of this vector? Direction of A, am I right? We are going to write that projection vector like this, B cos theta multiplied with A cap. Is that okay? Speak out. So again, we call this one as what you call vector projection. Is that okay? Projection of B on A. Vector projection of B on A. Can I say like this? Vector projection of B on A. Is that okay? Which is a vector, okay? This was a scalar actually. We call this one a scalar projection. Or projection length, can I say like this? So usually whenever we say projection of a vector, okay, so usually that is a vector actually. again, this b cos theta was a projection length actually. Either can I say like this, that projection length is a better word, isn't it? Or scalar projection, that's another word. Is that okay? So now from this equation you can see here b cos theta. If you need scalar projection or projection length, what would you do? You do a dot b divided by, you can take a here. Can I just rewrite this one? A divided by magnitude of a dot b. What is this one? B cos theta. This is equal to a cap dot b. A cap dot b. Is that okay? I will call this one as, look at here, projection length of b along a. Okay, can I say like this? Projection length of b along a, or projection of b along a. Can I say like this? Or projection length of b along a. Is that okay? So b cos theta into a cap. What is this one? A cap dot b vector into a cap again. What is this one? I think we have taken this one somewhere in case of LS coupling scheme. Do you remember? I have taken similar idea. This is a projection vector. Can I say like this? Projection vector or vector projection of b along a. That is this vector. Okay, I knew its magnitude. Now I have to give the proper direction. That's why I put a cap. A cap means magnitude of a. Sorry, a cap means unit vector along a, isn't it? Unit vector along a. It has magnitude 1. That's why it will not affect the total magnitude of this vector, isn't it? This is a unit vector. Okay, we call a cap as unit vector. I hope you know that one. Is that okay? So that's why. So let me generalize this idea. Okay, let me generalize this idea. This the generalization is, okay, projection length of vector A, some vector A, okay, along some unit vector n cap. Can I say like this? So that is equal to n cap dot A, isn't it? Projection vector or vector projection of A along n cap. Okay, that you are going to write like this: n cap dot vector A n cap. Can you grab this idea? I'm just generalizing this idea. Okay, here I have taken B on A. Here I have taken A on some arbitrary direction n cap. Is that okay? You may need this one. Okay. Find the difference. A cap here, not A vector. Okay, be careful. Okay, they say vector projection. Okay, I have taken it as a projection vector. I hope you are okay with that one. Okay. They say scalar projection. I have taken as a projection length. Is that okay? That is comfortable for me.
Sir?
Yes,
sir?
speak out. Yeah.
Sir, this last, this is projection vector of B along A. Sir, this one please define, sir, again, sir. This is also.
No? What happened?
The last one. Projection vector of B along A, sir.
A here, B here. I am talking about this vector. B cos theta into A cap.
But sir, B cos theta A cap is, sir, B cos theta A cap is itself, sir, projection vector or not, sir?
Yeah, that is projection vector. That's what I mentioned. Yeah.
Sir, if I will take the I cap instead of K cap.
Exactly. Again, we shall try to grab that idea, isn't it? Suppose if you write a vector in a Cartesian coordinate. Okay, suppose if you choose some coordinate ax into x cap plus ay into y cap plus az into z cap, okay, where x cap, y cap, z cap are orthogonal unit vectors. Is that okay? So then we call this one as projection length along x-axis, am I right? Projection of A along x-axis, am I right? But this whole thing is a projection vector actually. Now vector A is written as an addition of 3 vectors, am I right? Let me take this idea. So this is actually, so projection length on x-axis, okay? This whole thing is a projection vector. This whole thing is a projection vector along y-axis. This whole thing is a projection vector. You have added 3 vectors. Is that okay? To get a resultant vector. Or this vector is what you call decomposed like this. Is that okay? So now if you need AX, what will you do? If you need AX, what is that one? Projection length along x cap. Can I say like this? So if you need AX, what will you do? AX is, you are going to take dot product with x cap. That's what exactly I have done here. You need projection length of A along x cap, am I right? I have taken dot product with x cap. Similarly, I need projection length of B along A vector. I have taken dot product with A cap, exactly similar. Okay, I'll come to that point. This is a projection length. If you want to write a vector AX into x cap, how do you write? Just multiply with x cap. Isn't it? This is a scalar x cap, that's it. Isn't it? That's what I have done here. We did this one already. Is that okay? But you need to observe this one because it is required somewhere, okay? Speak out. Is that okay?
Yes, sir. Yes.
Yeah. I'll come to this point. One more small thing, distributive law. A dot product with B plus C. A dot product with B plus C. Is that okay? How do you write this one? A dot B plus A dot C. Dot product is distributed, isn't it? Among B and C, you can say like the distributive law. Is that okay? Yes. I hope these are not a big deal for you. And one more, okay? Yeah, speak out.
But almost 1 hour.
Wait a second. I'll take 10 more minutes. Let me finish off this idea. One more thing here, law of cosines, okay? Law of cosines. Law of cosines. There are 2 things here. Let me work out this one. We have vector A here, okay? Vector B here. Vector A here, vector B here. C is the resultant of the vector, am I right? Let me draw it as a dot, okay? This is C, vector C. Is that okay? C is equal to A plus B. Can I write like this? C is equal to A plus B. Now I know the angle between A and B. In this situation, I know the angle between A and B, okay? I know the magnitude of A and the magnitude of B. I know the angle between A and B. I need magnitude of C. Whenever we need magnitude, what we should do? Just I told. Speak out. You should take dot product with itself. What we do is, I need magnitude of C. To find that one, I'll take dot product with itself. Am I right? Can I call it as C square? C square, magnitude square. What is C dot C? There is A plus B dot A plus B. Is that okay? A plus B dot A plus B. Is that okay? Now again, you can just use your distributive property, this kind of thing. Am I right? A plus B dot A plus B dot B. Again, you can use distributive property. You can write like this: A dot A square, B dot B square, plus A dot B plus B dot A. isn't it? It is commutative. A dot B is same as B dot A. So can I write like this? A square plus B square plus 2 times A dot B. Or you can write C square is equal to A square plus B square plus 2AB cos theta. Suppose if you know the angle between them. Do you know in case of LS coupling we have used the same thing, isn't it? In case of quantum mechanics, isn't it? Speak out. Is that okay? So that is one idea. Just work it out yourself later. Okay, it's very simple. Theta is the angle between A and B, like this. That's what here it is defined. Okay, so do it yourself. Do it yourself. Now I have vector A. I have vector B. Okay. I told occasionally you may need to define this length. Am I right? Isn't it? I told you occasionally you may need to define this length. Okay. Let me call that one as vector. What is this vector? A minus B. Speak out, anyone? Is that okay? This vector is A minus B. Let me write C is equal to A minus B. Okay, this vector C. And occasionally I need, okay, I mean in the application later, I need this length. So C is equal to A minus B. I need length of this one. To find length of this one, what I do? I take dot product with itself. That's equal to length square. This is a length square, okay? Now what is this one? A minus B dot product with A minus B. Is that okay? A dot A minus of B dot B, isn't it? A square plus B square. Can I write directly? Minus 2 times A dot B. Or C square is equal to A square plus B square minus 2AB cosine of angle between them. Or C is equal to under root of A square plus B square minus 2AB cos theta. Okay, you are going to use this one somewhere. Okay, you can call it as law of cosines. Is that okay? What is the application of this dot product? Can you quickly tell me what is the application of this dot product? I mean, in case of mechanics, you can take, isn't it? Work done, that's equal to force into displacement. That's how you write, am I right? Force into displacement, isn't it? But our main application of this dot product, okay, along again, we do like this, okay? We are going to use like this also, okay, as a dot product. Most of the case, this dot product is used to define flux of field, suppose electric field. Flux of electric field through some what you call surface area. Is that okay? We write that one as E dot A. Let me define this one. Okay, I need vector field idea. Okay, to define that one. Let me define it later. Okay, we use this dot product like this actually, where A is an area vector, which is perpendicular to the surface area. Okay, so flux of electric field we say like this, where E is the electric field. Okay. So flux of magnetic field B dot A. Okay. Not only that, again we define some more here. So sometimes we need we define electric field dot product with elementary length actually. Dot product. Electric field dot product with small length vector. Okay. DL, and we are going to integrate this one. We call it as line integral. Okay. So there we use this dot product most of the case in the application of electrodynamics. Okay, yeah, we shall see that one. Okay, first let me define vector field idea, then let me define this flux idea. Okay, so that actually this flux of electric field E dot A, so this is proportional to number of field line passing through this surface area A. Proportional to number of filled line passing through the surface area A. We shall see that one. Let me do this interpretation later. Okay.